So I assume that you can see my screen. That's visible.
Yes, sir.
Okay. So let's start from and let us see in between that what we have understood about this transformer network. So transformer, we understood that we wanted to do sequence to sequence modeling. And in order to do sequence to sequence modeling, you somehow have to understand that there is some amount of temporal dependence, and whatever the word which is upcoming, it is there just because of the fact that whatever we have seen till now. So there is a context that need to be somehow learned, and depending upon the context, uh, next word is going to be appearing. But in order to learn such context, one way was recurrent neural networks. And we have seen that how we can use an encoder decoder type of model in order to realize sequence to sequence modeling. And later we have seen that it is sequential, so it's going to take good amount of time to train such a network. And then we started to see about the self-attention mechanism. So about this self-attention, we wanted to say that I'm going to have xi and I'm having yi. So whenever I'm going to predict any output, I wanted to know that how much amount of weight I should be giving to this guy, to this guy, to this, and to whatever we have seen till now, whatever that you have seen. So you see t things, you predict t or more than t or whatever, but whenever you are going to predict any output, you wanted to find out that how much amount of weight one should be giving to all of them. So suppose that there is someone who can give you such a weight, then it becomes very simple that any yi is going to be equal to a weighted sum, weights being decided like this. Suppose that somebody has given this, then weights are being set like this, and for every input sequence, you keep on multiplying with its corresponding weight and add so as to get the final output. And your each x is input is actually a t-dimensional vector, and in such way you are having k dimensional vector, and each and every vector so how many such xi's you have, so t such xi's we have. So this is the data matrix that we have, input matrix. And similarly you are going to have output capital Y matrix. What's going to be the size of your W matrix? W matrix is in, so your W matrix is in T by T form, and which is essentially nothing but going to tell you that while generating any yi, say y1 or say y2 or say y3, so given any row, if you wanted to generate that yi, y1, y2, y3 or any yi, then how much amount of weight you are going to give to this guy, give to x1 or to x2 or x3 or x4 and so on. One should also have to understand that since it's going to be used for the weighing, the summation of all of them should have to be equal to 1, because it's going to be some sort of probability distribution. And probably you can see probably at some, yeah, here I have shown that suppose that these are your x1 and x2 and x3, three things, then all yi's are actually going to be some sort of linear combination of this x1 and x2 and x3. And the only thing is that the summation of all these wij's is going to be equal to 1, not wij, basically w11 and 12 and 13. So call row wise, they are going to be equal to 1. So they can actually be seen as, you know, some point in this space of x1, x2 and x3. If these being seen as three basis, or forget about basis, just see that this is suppose that your x1, then x2 and then x3, and see these three things, and the space spanned by these three vectors. any point yi is actually going to be a linear combination of these three. So whatever the points that you are going to get over here, here, or whatever the places, they can actually be seen as the yi's. Is another way that you can see this stuff. But now the point comes that suppose that somebody has given you these weights, then how you can make these things, summing up to equal to 1. So there are multiple ways, but when we are going to talk about in deep learning, as well as these things are going to be between say 0 or 1, what you can do is that you do the softmax over this. So whatever the values you have got, you apply softmax row wise, and these value becomes between 0 and 1. And if this value is high, then it may get 0.9 and others will get very small values, but you add all of them and value is coming on to be equal to 1. Now the thing which remains is that suppose that you have got this W matrix, then what can be this function between xi and xj? Because here if I say wij, then it's actually talking about y2 and x2. This is for y and this is for x. Rows, so rows are actually for y's and columns are for x. That's why you can see that for each and every column 2 is fixed, because that is for x2. So what can be the meaning between what can be the function? So before the function, we need to understand that what is the meaning, and the meaning is that while generating y2, you are using x2. So here it's also telling that what is how much amount of relatedness is there between x2 and the x2. Here it is how much relatedness is between x2 and x3. How to find out a relatedness between two vector? We all understand that two vectors can actually be related and can be find out in multiple ways. One such way is actually their dot product. So once we have got this dot product between them, these xi's and these things, they are actually not normalized. So this value can actually be between anything between minus infinity and infinity. So you can have that. So you can have like this minus infinity and infinity, and you apply softmax over this row-wise normalization. And if I show you this thing again, just you are having x1, use another color. You are having x1, then x2, then x3, and then x4. And I'm generating y1, y2, y3, and y4. And right now what I'm generating, I'm only generating y4. So while generating y4, you are using x1, x2, x3, and x4, all of them. And it's going to be a weighted combination of x1, x2, x3, and x4. And how it's being done is that because you are generating y2, so x2, the relatedness of x2 is being checked with x1, x2 is being checked with x2, x2 is being checked with x3, and x2 being checked with x4. And you find out this weight W21, W22, W23, and W24. And that is the definition of any Wij. And you take this xi, multiply by this weight, x2 multiply by this weight, x3 multiply by this weight, and x4 multiply by this weight, and add all of them, and you are going to get y2. Is there any problem till now to any of you? Anyone can ask. No problem, then it is good. And and we are talking about permutation EQ variance. And several guys actually last lecture got slight amount of confusion, and they said that the point is that If I give as a sequence, if I give x2, x3, x4, x1, x2, x3, x4, or if I give x2, x1, x3, x4, or any permutation of such sequence, no matter what sequence or what permutation you are giving, you are going to get x1, x2, x3, x4 same, but in some other permutate form. So some of you actually got confused in between that whether it's going to happen or not. And let us do it in this way, that all of you need to write in your copy, and I'm going to ask, I will give you some time, and after that, one by one, I'll be asking, and you will have to, in your copy, you will have to write. And you will have to show it on your mobile phone or whatever camera that you have. So you'll have to on your camera, show whatever you have written. The question that I'm going to ask is that my blue sequence and my red sequence. Blue is I am going home. Please write it down. Blue is I am going home. And red is going I home N. Both of them are actually being, if you see them as a set of 5 elements, both of them are exactly equivalent to each other. And if they're exactly equivalent, transformer is also going to give me equivalent thing, because transformer is going to get or see the things in the form of sets. But semantically, they are completely different. And one should have to understand the fact that whatever you are going to get from this and whatever you are going to get from this, both of these things are going to be exactly same. How? That's the thing that you will have to do. I'm going to show you maybe for one thing, you will have to show me for rest. Like just concentrate on blue color things, wherever I have written. I am going home. That is why it is x1, x2, x3, x4. I am generating y2. So if you are generating y2, then x2, x2, and x2, and x2. x2 is going to be m, and m is here, m is here, m is here, and m is here. What is going to be x1 or x2, x3, x4? It's going to be I am going home. Now you multiply am and I. I am assuming that we are multiplying the embedding. You just write am or I. So how can I write? So when I generate y2, and I'm generating this y2 for, I'm generating y2 for my blue sequence. Then it is m multiplied by I, m multiplied by I. You have got the weight, and then multiply it by I. The weight of the embedding of I, and you will get the contribution that this x1 or I is going to have over my x2. Then I'm multiplying m and m. So m got multiplied with m, and whatever the weight that you have got, that's going to be multiplied by m. Third is m got multiplied with going, m got multiplied by going, and multiplied by going. And then finally m got multiplied by home and multiplied by home. So m got multiplied by home and home. Now yes. So similarly, what you can do is that, can you tell me, or first you write y1. First you write y1 in your copy the way in which I have written, first of all. I assume that you all can understand, and I'm giving you time. y1 you will have to write. It is being written in this way. and y1 for blue. Y1 for blue like this. This is going to be the expression for y1 for blue. I assume that you all can write. As soon as you write, please write that in your chat that you are done. Please do not copy from here. You write on your own. If you are having any doubt, then you can ask. If you are done, then you can write in your chat. Yes, sir. Chandresh Kumar. Good. Only one have done. Please write you are done. Pratik, done. Manuvendra, done. Good. Understood. Understood. Fine. Okay, good. When it is done, next step is now for this red. You get this red thing. Going I home am. Now this for this for this red, I am computing y2. Please write it down. I'm saying that for this red, you have to write y2 and tell me what you have observed. For this red, all you have to write y2. This y2 is for blue sequence. This y1 is for blue sequence. And I wanted to know y2 for red sequence. Y2 for red sequence. Once you write it down, please tell me your inference. Ankit Katyar, it is done. Gitanjali, it is done. Write down the y2 for red sequence. Same with Chandresh. It is same with whom? Write in the chat. Yeah, same as y1 for blue. Correct. y2 of red is equal to y1 of blue. Perfectly correct. Now, Anushka and Arjun and all, what you will have to do is that you have to tell me, write it down like you have to write it down like for blue y1, y2, y3, y4, and for red y1, y2, y3, and y4. And as we all understand that they are same, can you tell me remaining three, they are same to whom? First, let's figure out that you need to tell me that this y2 is same to whom? This y2 is similar to y1 or y3 or y4?
Y4.
Y4. Y2 is same to y4. Y2 is same to y4 is correct. Y2 is same to y4 is correct. Y3, let us go and talk about y3. Y3 is same to
Y1.
y1. And y4 is same to y4. I assume that we all have got this. There is a small little exercise, and still if you are not able to figure out, I seriously and sincerely request you that you need to understand this stuff. That is why I extended my last lecture to this, that please understand the positional information is not taken very seriously by transformers, and this is going to play big problem, because if you show something and if you show a permutation of that, same things are going to come over there, but this is incorrect. Network has to understand the context, because in the case of words, in the case of sequences, position is going to matter really very well. It has to be somehow very well addressed. In chat box, if you understood the concept, you write please yes. I want to see yes. Positional equivariance is not desirable. permutation equivariance is not desirable, positional invariance is not required. Because if it is there, then any
Sir,
permutation is going to give me the same thing. Yes, Anusha.
sir, we got the same words, but the order is different.
Yes, the order is going to be different, but you can see that y's are actually, you are getting the same y's again and again.
Hmm.
But same y's are not desirable, because suppose that I wanted to say that teacher has given me the assignment, and then if I somehow change the sequences, then the output that you are going to get is something absurd. Doesn't mean. Semantic is there because of the semantic of any sequence is there just because of the fact that they are in a proper order. Now suppose that I take such a model and train something and started to write a new novel for you, then what will happen that sentences, you are going to get sentences, but the ordering of the word is probably not correct, and then you will not be able to figure out that what does it mean. Semantically, I am going and going I am, they are completely different, but network is saying that they are actually in a, there is no position involved, and because of that you have to figure out that what has to be the correct position, which is not desired.
Okay. Okay.
Yes, anyone else want to comment on this? This is a small exercise I wanted to do so that we all can understand the fact what is happening, and because to handle this we require certain other things. Are you done with this? Okay, make sure that you are done with this. Yes. So why do self-attention work, we all have seen in the last lecture, so I'm not going to repeat this, but the thing that I want to somehow say is, yes, so now we are going to talk about the realization of such thing. So before that, let me ask that how many parameters transformer need to learn? Anushka, can you tell?
So the weight matrix of T is T cross T, but I see that it is made from the same Xi by Xi matrix, so probably the half of the matrix of the weight matrix.
Half of the weight matrix is being learned.
Right.
Ananya, you tell me. Ananya, you tell. Ananya, are you there?
Hello.
Yes, Ananya, tell me.
Yes, sir. The weight matrix has to be learned.
Weight matrix has to be learned. Okay. Arjun Sahadev, you tell me.
So the weight matrix has to be learned like full run.
Weight matrix, T cross T values you need to learn.
Yes, sir.
Okay. Lokendra, you tell me.
Yes, sir. When we study three counties, like weight matrix,
Do you want to say that weight matrix need to be learned? Your voice is cutting. Let us go and ask Anurag. Anurag, are you there? Anurag is not there. Let us ask Pratik. No, wait. Let us ask Rishikesh. Rishikesh? Yes.
Weight matrix.
Mute. Manvendra.
T cross T weight matrix.
Acha, if I say that it is wrong, can you justify why it is wrong?
Sir,
Yes.
So t cross t minus t divided by 2 plus t.
Okay, let us go and talk to Prateek Jain.
Yes, sir.
You tell me how many parameters I need to learn for transformer.
Sir, I guess no parameters till now because all
Yes,
parameters are decided by the dot product. So no parameters to be learned.
भैया सब लोग समझो ना. You all have to understand. You are trying to go with only whatever I am saying. You have to apply because that is what now you see. आप ही ने इसको बनाया ना ये पूरा. I have only said that embedding is there and you are assuming that this is available, everything is available. So word embedding has given you, and for word embedding, I am not counting the parameters because it's a different network. Transformer is only doing what? Weight matrix. Weight matrix is just the dot product. But till now, nothing we have learned. Transformer requires no weights at all till now. Is this clear? Crystal clear to everyone? Right in your
So means
chat
we just have feed forward network here, nothing else.
even
Only
there
in
is not
forward direction.
no even there is not even a feed forward network. It is just the flow diagram I just have shown you. This was just a computational flow diagram. There is no neural network involved till now. Where is the neural network? You are having this value got multiplied by this, you have got this value and add and do this thing. Whatever I have written in or shown in this diagram, you can see that's already being written over here. This is one single formula. This is that formula for you. I'm applying this formula for you. You can see this thing now. Weighted sum. Well, just a weighted sum, I've shown it to you. Nothing more than that. No parameter, no even feed forward, nothing, no network. Is this clear to everyone? You can write in your chat. In chat, only one has written t plus t by 2 parameters is incorrect right now. And yes, Chandresh is saying Ankit Ashima. Good. If there is anyone who is not able to understand the fact, please ask me again. I'll be slow because I want all of you to really understand the fact about the transformer. All the new work, I mean transformer I have not covered in my previous last offering. And this is a very, very new recent advancement. All of the recent papers, most of, if I say, wherever they wanted to use some sort of temporal dependency, they are using transformer. Starting from transformer, then BERT, then GPT-2, GPT-3, and long formers. There are so many versions of this. A huge amount of work is essentially being happening in this area of using transformers. So we need to really understand the crux here. Yes.
The vector dependence is already there. Like we already know how the words are related.
Yes. Yes. Word to vec is doing that thing.
That is already known. Okay.
Yes.
Okay.
That is being done by word to vec embedding or glove embedding or any other embedding that you are using. That is not the responsibility of transformer. Transformer's responsibility is to understand the context, and to understand the context that is being seen till now to generate y2 or yi in the best possible way. And it is saying that I am going to use only one very simple single small thing like this. And the interesting thing is that this is, you can see that huge amount of computation is anyways being required, but being a multiplication of certain values with the vectors, its whole thing, whole yi can, or all the y's can actually be computed using some matrix multiplication. And matrix multiplication is heavily parallelizable. So because of that, its training time is much, much lesser than recurrent neural network. Yes. So here, so let us see one more time that what we have done till now. And here comes that when I say that transformer do not require network, that's a plain transformer that's not being used. And now I am going to tell that what a transformer requires to be learned and where are these parameters that need properly learned, that need to be learned properly. So I am having x1, x2, x3 and x4. I am generating y2. You all understand. Then the embedding of x2 is going here, is going here, is going here, and so on. Let us see it once. What is happening is that that I have got for every xi, which is going to play or can be going to be used to generate y2 or any yi, whatever the xi's that I have, all of them are going to play three different roles for me. Same xi can once be used as a query, can once be used as a key, and can once be used as a value. Three things. Why, we will talk about this. But first let us understand that what is the interpretation of a transformer. One is query. Please write down in your copy. Query, key, and value. This xi or x2 once being used as, or sometimes be used as query, sometimes be used as key, and sometimes be used as value in transformer type of network. Now what does it mean? It is very, very simple. Let me show it to you. That when you are using when you are generating y2, then x2 is being asking to each and every word that are you similar to me, and that is actually the role of x2 as query. Let me rephrase it, that when you are generating y2, x2 is going to ask to each of my x1, x2, x3, x4, how much close you are, how much related you are with me. And once you have got that, that is the weight that I am going to use. Fine. But when you have used this x2 in this way, this is actually querying. So x2 is querying to each and everyone for the relatedness. So that is why you see that x2's role number 1 as query. x2's role number 1 is that asking everyone that as a query, that are you similar to me? Are you similar to me? Are you similar to me? Now see that x2 is coming here, and that is actually the role of x2 as key. When somebody asks you for your relatedness, then x2 is actually being converted into a key. So the first role is that x2 is asking to everyone, and x2 when it's asking, other guys are not coming into its true color, they are actually coming in its transformed version, or the role is actually key. So this is a key role. So x2's first role is this, x2's second role is this. And where is the x2 third role? x2 third role is here, being used as the value. You can use the embedding at its value as its value, or you wanted to learn another linear transformation or some non-linear transformation which will take the embedding of x2, convert into certain other thing, and that value is actually being used as the value for x2. Let us restate the word statement, that any xi is going to play three roles. One is its query when it is asking to everyone, and when it is going to play a query. So any xi is going to play a query when you are going to generate yi. From xi, when you are generating yi, then xi is going to play the role of query. At any point of time, whenever as any input you got a query, you are going to give your key for checking that how close you are. So that is the role that at any point of time any xi is going to play. So what is going to happen is that any x1, when x1 got a query, it is going to respond by its key, and the distance or the dot product is being computed between the query of x2 and the key of x1. Query of x2 and the key of x1. Once you have got this, now it remains that I take this embedding and I have got the how much amount of weight one should be giving to this embedding, and I can multiply it directly. Instead of that, I am saying that I convert this x1 into another of its role, and that role is actually the key role. That role is actually the value role. So your value is not even your embedding. Your value is a transformation of your embedding that is going to be multiplied over here. So if I write it in another way, that any xi, let me write it in a bigger font, that any xi, it is going to play a role like query, playing a role like key, and going to play a role like value. And just see this xi as you. Suppose that you are a person, xi is actually a person. So in your real life also you are playing multiple roles. Sometimes you are son, sometimes you are daughter, sometimes you are friend, sometimes you are teacher, sometimes you are father. So many different roles in a life you are playing. Same to you, xi is also being designed to play three different roles. And in all of these three different roles, your embedding, if I write the embedding as E, let me write that embedding as E, your embedding, or as a sole person, you remains to be the same, but your embedding is being transformed into this, into this, into this. Why? So as to manage the context in the best possible way, because otherwise it is not possible for a single person to behave equally in each and every role. When you are son, still you are ABCD, you may be director of an institute, but in front of your father you behave in a different way, in front of your mother you behave in a different way, in front of your wife you behave in a different way, and along with your son you are working in a different way, along with your student you are completely different. So same thing, but multiple roles. In case of transformer, they have designed it to be working in three different roles. You may say, why only three? Probably they understood that using three, three ways we can get the better or optimized efficient solution. Probably you may have 5 roles or 10 roles or whatever. But having more and more roles make it more and more complex and more parameters to be learned. But using this key, K and V, you can see it in this way. Why these things are completely different? That suppose that you are XI or EXI and you wanted to ask money with your friend. So in this way, suppose that this is X2, you want money, and that is why it is querying to each and everyone. So when you are querying, you are in a completely different mode. So the same guy X2, while querying, is a different transformed version of this X2. But suppose that some guy is standing in front of you and asking money from you, then you may behave in a different way than when you are asking money. When you are asking money, so when X2 was asking money, This was its role. When XQ was actually asking, responding to whether it is same or different, or whether you are going to give the money or not, you will sometimes say that, no, I do not have money. Or somebody will say that, I have, but how much you want? Somebody will say that, no, I am only able to give you 500 rupees. So it depends upon each and every guy, depends upon each and every word, that when it is asking, how it is asking, when it is responding to that query, how it is responding to that query, and how it is using its own value, its own embedding, how it is going to use. You are free to use your own embedding in the whatever ways that you want. So in this way, if I show that how to, so what is going to happen is that when I say that you are having 3 embeddings like this, so you have actually one embedding which is being converted into 3 different embeddings. You need to learn these embeddings, how to convert this embedding into an embedding that is suitable, most suitable for key. So when you are going to when you are going to ask for query, you have to be very in the best possible way. You are going to ask in as polite way as possible that, do you have some money for me? I am in some need or something. So the way in which you are going to convert your vector into query, you need to learn. Then you require, how can I convert myself into a role when somebody comes and asks for money? Then you will see that, oh, you started to behave in a very different way, and that is the transformation one should need to learn. And similarly, one should need to learn how I am going to use my own values. So in this way, there has to be certain different 3 neural networks, and they are going to be a fully connected network. They will take a k-dimensional embedding and going to give me a k-dimensional output embedding. Can anyone tell me that how much amount of parameters are involved in this type of network, which is taking k-dimensional input and k-dimensional output? How many parameters do you require? There are so many different ways in which this can be learned, but suppose that if I say that I am having only one matrix W that I am going to learn, that is WQ. If I learn only one single WQ matrix, what is the size of this WQ matrix?
K cross K.
That is going to be a K cross K matrix, which is going to be multiplied by the embedding of any Xi, which is a K cross 1. And when you multiply, you are going to get some the query value of Xi, which is equal to K cross 1. Same is going to happen, and it is going to be a K cross K matrix. This is also a K cross K matrix, and this is also a K cross K. 3 K cross K matrix need to be learned that can convert my embedding into 3 different things. Is this clear to everyone? You can ask in between if you have any doubt. Otherwise, let us see this diagram, which is very straightforward right now. That when I'm generating X2, I am getting the contribution of Y3. How? So from this X2, you are getting a, so WQ, WQ, WK, WV. These are 3 matrices and they are fixed. We learn and they are fixed. Once you have got this, you wanted to know that what is the contribution of this guy in this. How you can get that? You take this, multiply with X2. You will get the query value of this. You will take this, multiply with WK, you will get the key value of X3. Query of 2, key of 3, multiply, you will get weight that you need to give to X3. Now X3 is not directly going. X3 got multiplied with its value. matrix, you will get the value or the value role
Finally.
of x3, and then you multiply. Is this clear to everyone? Yeah, anyone want to say anything? Okay, so in this way x3 got its output, and the same way all of them are actually getting the outputs. So if I wanted to find out that what is the contribution of x2, x4, it is straightforward. What it is, that you take the x4's contribution in y2 is going to be query of this got multiplied with the key of this multiplied with the value of this. Is this clear to everyone? You can write yes in your chat box. Chat box, write yes. Vaibhav ne kaha yes. Anyone else who want to say yes, or if there is anyone who is not able to understand, please say no. Tanya. Yes, yes, this is clear, I assume. Ashima, fine. So now you see it's being written multiple times that x3 is going to play role number 1, role number 2, and role number 3. First role is in the query, then the value and the key. This is straightforward, very much clear. All the things that I have explained, everything is written over here. And it's again being explained that for y1 computation, x1's query, for relatedness using this. So when you are computing y1, x1's query is going to be used. Key of every other is going to be used. And the contributions, individual contributions, are going to be multiplied with the weights that you have got with the individual values, and then you will get y1, y2, y3, and y4. This is again very clear, straightforward, and okay for you. So we already have seen this formula. This formula is not being changed at all. Everything remains to be same exactly like this. Only thing which is being changed is that yi's are actually going to be, these weights are not going to be generated using, their embeddings, or the embedding relatedness between x1 and x.
Have a clue?
Mute your mic, please mute your mic. Xi, and so any wi comma j, it's now going to find out the relatedness between the query and the key. This is the query, that's the key. This is the query, that's the key. So if I say that W32, what does it mean? W32 is going to say W32 is going to say that the query of 3, key of 2 got multiplied, you have got the weight, and you multiply the value with that value of x2, multiply, and you are going to get query this, key this, multiplied with the value of x2, and that's the contribution of y2 in, say, y3. And you can see that the contribution of x2 in y3. Yeah, that's straightforward. I assume that I explained it 2-3 times. The same thing is actually being written in order to just make sure everyone that understood. Now let us see that what is going to be the final algorithm that is being used when you are training self-attention. Till now it is not a transformer. This is only we are talking about self-attention. Self-attention layers are going to be used so as to realize transformer. So given any xi, first I find out its query, then its key, then its value using these matrices. And these matrices are fixed. Any xi you give, I multiply by this, I am going to get the query, the key, and the value. Query, the key, and the value. Then any weight, how I am going to get? query multiplied by the key. So query of I multiplied by the key of j. I've got the full matrix for all ij's. I softmax like this. Once I have got the softmax, what is going to be, this is the basic formula we already have written previously. That is my self-attention, that the contribution of j in making I, contribution of j in making I is this, and how you will get the value. So how you will get yi, that all the contributions got multiplied by the corresponding values and add, you will get all the yi's. Yeah, so if there is anyone who wanted to ask any question.
So,
No. Yes.
this is a question which I have from a little ahead. Like when we are generating the embeddings, we are generating it prior feeding it into the network. Then we are
Yes.
calculating the weights using those embeddings.
Yes.
Now the question is, sir, from that, when we are taking the dot product of those embeddings, then we are
Yes.
estimating the neighborhood, how close they are. But
Hmm.
that information has to be there in the embedding first, right?
So it is there in the embedding. Yes. Embedding
Because I
is
feel in the we are just arbitrarily embedding it. So,
yes. Yes. OS is cutting. Yes. Yes.
so I'm saying that if we are multiplying two things which are like we are encoding it prior any kind of training or anything, we don't have neighborhood information in them. So how can we rely that on that multiplication we can say how close or far apart they are from each other? From
Oh, no, Anushka. Probably you forget. Let us open the yes, word embedding thing. How this word embedding network is being trained, you remember? Word to, where was that word to work embedding? Yes. So in that word to work embedding, no, is it the word to work embedding? Where is my word to work embedding? Let me open it once. Word to work, I forget where it was at that point. Is it here? Yes, so it is here, and we train it over n-grams, bigram, trigrams, and some context. So depending upon that context we have trained, but this is general context. This doesn't depend on, rely on the context or the problem that we have in our hand. So they require, word to vec require neighborhood, and this neighborhood is properly being encoded using word to vec. Otherwise it will not be able to train. But in general, what happens is that once you train such network, they are general network, generic network. And using that generic embedding may not be very useful or feasible in your context, because the type of words and the type of data that you have, probably it is having a slightly different type of context. So you want to fine tune those embeddings. That is why instead of using one fixed embedding, I am converting that fixed embedding into 3 different roles. And we are learning how to convert such things into different things. Do you understand now?
probably I missed this part out because of network disturbances.
Oh, because of network disturbances. So that's why I'm saying that word embedding is having its own context.
Yes, sir.
So, and it's being trained over global context. Fine.
Yes,
So
sir.
it
I
is not.
agree to that.
Okay, fine. I assume that you understood the fact. Anyone else who want to say anything? Any comment? Okay. Now, that's another trick that's being done here. And that is the scaling the dot product. And how can I scale a dot product is that when you do this dot product several times, what will happen that that because this dot product is high. Why this dot product is high? Suppose that you are using 10-dimensional embedding and someone else is using 20-dimensional embedding. Somebody else is using 30-dimensional embedding. So the one who is having 30-dimensional embedding, it is going to get a bigger dot product. No matter how close two vectors are, but because there are 30 things which are going to be multiplied and added, and because here in 10, only 10 things are going to be multiplied and added, your values are actually being governed by how many number of values you are multiplying. And that is actually your dot product is becoming bigger and bigger, no matter how related they are. It is slightly bigger just because of the fact that the embedding dimension is bigger. Somebody is using 128-dimensional vector, someone is using 10-dimensional vector. So in that case, the value high or low is not going to play a very significant role. And then one should have to do it in this way, that per unit dimensions, per unit dimension, we are going to normalize it. And you can see it here as well, that suppose that I'm having a k-dimensional vector. I'm having k-dimensional vector. Given this k-dimensional vector and all these values are C. And suppose that if I'm having k-dimensional vector, then what is going to be the norm of this k-dimensional vector? It's going to be root k times C. I wanted to, and this norm is actually going to be dependent upon root k, by which it's actually growing. If it is not k, if k is equal to 10, then this is root 10C. If it is 15, then it is root 15C. If it is k50, then root 50C. And this value is keep on growing. How can I normalize? I can easily normalize using just divided by root k. And that is why this is the second trick that's being done, using normalizing by root k, number of dimensions. Let's go and talk about a very interesting and most important part of transformer network. Or sorry, that not the transformer. Till now I completely, several times I've said transformer, but till now I have not even talked about transformer. We are only talking about self-attention till now. So given a self-attention network, we have understood that for every word is going to play 3 different roles. This is the first thing. And there is going to be a linear summation of the contributions that we compute and multiply with the values. And relatedness is being computed between query and the key. Now let us see. The teacher gave homework to a student. This is case number 1. And my case number 2 is student gave homework to teacher. Both of them are exactly same, but the sequence of word is actually being changed. And if the sequence of word is changing, the whole context and the meaning is actually also got completely changed. Not only this, suppose that I have a word, I have a sequence like this. This is a big sequence, and I'm assuming that there is some context. Where this context is actually being learned, this context is being learned between WQ, WK, and WV. This is actually a matrix which learned a context that how can I convert any xi into its query, into its key, and into its value. How can I convert them one by one? And that is the context. You understand, depending upon the context, depending upon this word is going to behave depending upon the context. And who is going to tell that what is the context? These guys are going to tell that what is the context. And this context is learned by seeing full complete input sequence x1 to xt. When you see all x1 to xt, you understood that what is the context. What is x1? This is x1. What is xt? This is xt. So you have seen all the context in between, all the input, and then you come up with this and this and this. And this is the context that's been got embedded in these vectors, in these matrices. And now you can somehow, use the self-attention model to generate the corresponding second sequence. Now see that if you see whole thing, then give is going to have a type of context. So if you see first this, then you see second this, and this is one single thing. This is sentence number 1, this is sentence number 2, and both of these sentences are being shown to the self-attention network. So sentence 1 and sentence 2, both of these things are actually concatenated, and that is the whole corpus. So you see the whole corpus at once and find out that what is going to be when I give gave, what is going to be y gave. And y gave because my WQ, WK and WV are fixed. So y gave is not going to be any different. Whatever you are going to get y gave over here, the same y gave you are going to get over here. And if the same things are going to be there, then the meaning of both of these gaves are going to be exactly same, semantic meaning. But you can see here that this gave and this gave is actually different. This is actually given by teacher. This is actually given by student. And this is actually being true in most of the linguistic, because the same word is going to happen into multiple ways. Is there anyone who want to ask anything? Yes? If no, then please mute your microphone. Yes. So the point is that the same word means differently to its neighborhood and the context. Same word behaves completely different depending upon its neighborhood. But if you have only one context that's going to be learned, then all words are actually being fixed to be learned as one context. And then what is going to happen, that the averaging of context is going to happen, because only one thing that you can predict, give and gave, and the average of this and the average of this is going to be here as well as here. Yes, want to say anything? Please mute if you do not want to say anything. I request that if you do not want to ask any question, then please mute your mic, else I somehow got distracted. Now, now that is the point, that instead of going for only learning one such context, can I learn multiple context? So if I say multiple context, this is going to say that I am learning heads, and this is one head, which is a context. I'm having one head, I can have another head. So if I have another head, what is the significance or the physical significance of that? I am having another head is that WQ, WK and WV. I'm having another set of WK, WV and WV. So I am having 3 matrices. I am having another 3 matrices. I have another 3 matrices. Now gave will come here, or it may go here, or it may go here. So for this gave, probably this matrix is suitable. For this gave, probably this matrix is suitable. So you can see that the same word in multi-head attention can play 3 different roles in any head, but you can have even 3 different heads under which it can play different roles. And because of that, this linguistic constraint that words are completely different in their neighborhood, they depends upon their neighborhood. All the words are not, their meaning is not static. The words can play depending upon their context, and self-attention need to somehow handle that, and it is handling it via multiple heads. So I'm having head 1, head 2, head 3, head 4. I'm having R such heads. And what does they mean? I'm having WQ1, WK1, WV1, then 2, 2, 2, and K, 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 and R, 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 and so on. What this individual thing is, this individual is actually a K cross K matrix. This is the number of parameters that you need to learn. And in this way, you are having 3 times K cross K So 3k square parameters for a head, and if you have r such things, then this r. So basically you are having 3 times rk square number of parameters. In any network, self-attention network, in which you are having r heads and embedding is k dimensional. But how? So what will happen is that now there are multiple heads. How can I utilize all of these heads? Because I only let you understand that if you had one such head, how you can use this. If you have multiple heads, there has to be some way by which I can manage that. And the management is that x1, x2 and x3 will be there. They will go simultaneously to the different heads. Simultaneously going to different heads, you are getting different y1, y2. So all of them are actually going to give that what is the contribution, or one can say that when x1 goes in, you are getting actually multiple y1s. I concatenate all of them and show it to a network. That is going to learn some averaging, some type of combination between them, and the linear transformation is here converting different outputs that we are getting from different heads, combine them and give me, this is actually the combination, and shown it to a network and getting only single y1, because at last you are only going to get a single y1. So in this way, attention is also not only learning between the sentences, but as well as between the heads. So this network is trying to learn what amount of weight one should be giving to this or this or this, so as to come up with the best possible y. And same is going to happen for x2 and x3. So all of these x1 inputs are going simultaneously into all the heads. You are getting multiple y1s, multiple y2s and multiple yts. Essentially the amount of heads, that number of output you are going to get from any from any given input. If you wanted to only generate y1, y2 and y3, so let me write it that if you wanted to generate from x1, x2 and x3, you wanted to generate y1, y2 and y3. So instead of, and if you have 3 heads, h1, h2 and h3, then this will go and you are going to get y1, 1, y1, 2, y1, 3, y2, 1, y2, 2 and y2, 3. When this will go, and when this will go, you are going to get y31, y32 and y33, and I'm having a neural network here, I'm having another neural network here, and I'm having another neural network which is taking this and going to give me y1, y2 and y3. Is this clear to everyone? This is multi-head attention. One head, then multi-head attention. We are done with this. We are done with today's class. Maybe in the next class we are going to talk about long and what's that, narrow and wide attention.